Hi, everybody. Oh, I didn't mic check. Hold on, mic check. Mic check. Da 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 da. Da 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 da. That's a little bit. Okay. Oh, I gotta turn the music down too. Sorry. Forgot to do that. Hi, everybody. Welcome back to Chem 121, 161. I don't know what class I'm on. This is my third lecture of the day. What is this? 161. Hi, welcome back to 161. After I've been lecturing since noon straight, like I have had a 30-minute break and a 30-minute break, so I'm just like, whoa, where am I even? Like, what is this? Because of that, I know that. Let me go check my email really quickly. Two people sent me emails. One of them is in this class. And I haven't had time to get back to you. I haven't even had time to open the email, so I apologize. Tuesday is just kind of my shit day. I just have so much to do, so I won't be able to answer email until like 7:30. And it'd be the same if you messaged me in Discord, but you would very quickly get an answer back that just says, "Hey, I'll answer this later tonight." So I apologize if you email me and I don't get back to you really quickly. Then one of two things has happened: either I just gone to bed, or it's Tuesday. And Wednesday is kind of like that too, but I have a little bit more time on Wednesday for that. Down at the bottom, you can see that lab worksheet number 1 is due on Tuesday the 19th. We talked about the lab yesterday, so you know how to do it, hopefully, but make sure you ask me any questions that you might have, okay? What else do I have? That's really it. The first quiz will go up soon-ish. We might finish this today. I don't know. There's a lot of review that... sorry, that's my calculator. I need that. There's a lot of review that we're going to try and breeze through because this is all 140 sig fig stuff. Like, we know how to do this for the most part. Let's have a little discussion about what we are doing here, though. So, in chemistry, like a lot of science classes, so physics, biology, etc., whenever you make a measurement of something, you're going to be using a tool of some sort. And by the very virtue of how measurements work, they're inexact. You cannot land exactly on this 20 line. That is just not something that is possible. You can get really close, but how close you get is going to be determined by the other marks on the graduated cylinder. So whenever I make an estimate, of course, I am going to have some uncertainty, and I'm going to have to make a guess at what that last digit is. What could it be? So in this example right here, I've got a number that falls somewhere between... Oops, that's not my pen, sorry. I guess it's coming up on the next slide anyway, so... What is the volume of this graduated cylinder? What is the correct number to report? So if you remember from 140, the correct way to do this is to find your marks, write down the value of the lower mark. Since these are all ones, it looks like, I would write down this as the value of the lower mark, and then guess the next digit in the next place. So that'd be the 10th place. This looks kind of like it's midway through. To me, it kind of looks like it's a little past that. So writing like a 5 or a 6 would be good. And then don't forget your units, because of course you want to have units here. See, I should have gone with my gut. I thought it was a little bit further, but whatever, right? Now, this lets us look into an issue with precision and also reproducible errors. I am the person who made both of these measurements, and I did not get the same answer both times. So, what does that tell you? Human perception is not perfect. And so that last digit, the estimated digit, so this is the estimated digit here, it can be off a little bit in either direction, but there are certain numbers that we are just going to exclude. Like that last digit could not be 0. That last digit could not be 9 or 8 or 2. But 6, 5, maybe 4? Probably not 7. Like there's a range of numbers that it could be. And then from that, we can then say that that number is fairly known enough that we can use it reliably in calculations. So, just in case you have forgotten the rules for measuring anything, here they are. Find your 2 marks, Write down all the digits for the lesser known, or for the lesser of the 2 marks. My text is behind that. Let me see if I can fix that real quick. Is that this one? If I click on this, send to back. Boop. Did that work? Oh, it made it disappear, but oh, shit. There we go. Okay. Apologies for that. I don't know why that was behind there. Write down the lesser of the 2 marks that you have selected. Make sure you write down all known digits, and then estimate the next 1 digit. That's how you do it. Okay. That should not be news or new to anyone, hopefully. But if it is, there it is. So I'm going to give you a few examples. I want you to try and do this. So I want you to tell me, looking at ruler A, what measurement you should write down using those rules, and then write down what you think you should measure with ruler B. Type your answers in the chat with your guesses, and don't forget units. So do that now. Now, while you're doing this, try not to look at the other people's answers, and don't redact them if you think yours is wrong, because I want to see if you get different answers. This is actually part of the experiment, so type what you think the answer is. Okay, that's good. So let's do this using the rules that we established earlier. So first of all, we're going to find the marks. So that's obviously these two. So for this rule, I'm going to write down the first digit that I know, and I only know 4, because it counts by ones. Then I'll guess the next digit. That's pretty close to midway. So that's what I'm going to write down, and that looks like we are all in agreement for that one. Over here, I wish I could zoom this in. I could zoom this in if I, if I do this. This is kind of a, oops. I gotta actually click on it before I crop it. So let's do that. We'll put what I'm writing on. Where is my writing? Oh, I haven't written anything yet. So now we'll just do this. Whee! Now it's really big and you can see it. There we go. And so now when I write on this, it should be ginormous. So now you can see that this... Oh, I should not look at that screen trying to draw. It's very disorienting. This is the, 1, 2, 3, 4, 5th mark. So I'm going to write 4.5 as my lesser of the two. And then even then, because I drew these pen marks in the way, let's erase those. Even then, it's still kind of hard to tell where it falls in. I'm going to just guess that it's slightly past here. And then when I hit the spacebar, inevitably I'll be wrong again. And look at that, I was wrong again. But was I really wrong? Not really, right? Okay. I'm going to have to reformat this screen really quickly, so I got to make it smaller again. So that I can then go like this. Whee! And then we'll just shove that up here for later use, because we're going to come back to this screen later. And then we'll just go back to here. So as you can see, adding more marks to my device or tool allows me to get a more precise measurement. And like, duh, right? If you have more dashes, it's a better tool. But practically speaking, using something like a ruler, you can only cram so many lines in before our eyes fail us. And so at some point, we have to start using mechanical devices, such as like calipers or a laser or something of that nature to get more precise answers. What about this? What the hell is this thing? I don't know. We've never seen it because we've never done any lab work in this class, have we? But this is a balance, just in case you've never seen it. With a balance, the balance is already doing this work for us. And so this last digit right here, I don't know why the hell this is in ounces. Who the hell uses ounces? But this last digit right here is our estimate. So what this means is that if this is our balance and it's like a needle pointing up and down on it, our scale would be something like this. So 21.16, 21.17, and it's going to say, oh, I think you're about here. This is the answer that I'm going to report for you. So the last digit is the uncertain digit, and it's already been taken into account. I wrote grams on here because I actually didn't see that it said ounces. We're going to make that grams. There you go. And it works up on the same premise. You can imagine a linear scale with marks that are much closer together, using some sort of mechanical apparatus or algorithm or whatever. And then you can get your result from that too. All right, so with that in mind, now that we know the common tools that we're going to work with, let's talk about what those numbers represent. We know what significant figures are because we've taken classes that have these concepts in them. For our purposes, sig figs represent numbers that you know for sure, or are that estimated digit. That estimated digit is known well enough such that we can rely on it for our calculations. So the takeaway from that is I'm going to write down numbers that I know, which means that any number I write down that isn't 0 is going to be a significant figure. I would only write down 4.56 if I know that 6 was reliable. If I didn't know it was reliable, I wouldn't write the digit. I would just write 4.5. Now, depending on how you write 0, 0 might be significant depending on how you use it or how you don't use it. And then finally, the number of digits that you write, so the number of significant figures, oops, my pen kind of slipped there, tells you how precise your device is. So for instance, something with 3 sig figs, not that great. That's probably a really shitty ruler. But something with 8, this would be like, I can't even imagine what would measure with 8. This would be something with like, maybe like an interferometer or like something to measure the wavelength of light or something like that. It would be much, much harder to do this, and we certainly couldn't do it with a ruler. All right. What's the 0 deal? Like, how do we deal with 0? Well, in our first example here, I've written some zeros down in this number. Do they mean anything? Well, if I did this to the number, let's suppose I owed you this much money, and I said, well, those zeros, I can't seem to select the right color here. Those zeros are placeholders. Oh, that didn't work. That's also the wrong color. My goodness. I'm trying to get it to select black so I can do this. That's not what I wanted. There, now I know I owe you no money. I've redacted everything. I want to eliminate these. So those zeros are placeholders. That's what I'm going to pay you. If I owe you $3,996 and rounded it up to $4,000 and then truncated those zeros because they're placeholders, you would be very upset with me. For which I could not rightly criticize you. Those zeros have a value or a purpose to them. They don't have a value, but they have a purpose. And that purpose is this number, as written, is just in the ones place. But if I add a 0 to it, this is now the tens place. And if I add another 0, this is now the hundreds place. And if I keep doing that, I change the place that it's in. So these zeros force this number to have the correct magnitude. Okay? So those zeros are important as far as magnitude is concerned. but the zeros themselves do not have a meaning for our measurement. So if zeros are used as a placeholder, they do not affect our precision. We ignore them, okay? 3,996 is a very specific number. 4,000 is very approximate. Here are some examples of some numbers that have zeros as sig figs. And the way that you can look at these is to say, if those zeros were crossed out, would the value of the number change? If the number does change in value, those zeros must be placeholders, and thus aren't significant figures. They're just there because they have to be. All right. Should be a review. Hopefully it is. Let me know if you have questions, though. All right, and that's what we just said, so let's go on. By virtue of numbers landing on a scale, if you happen to have a zero that lands between two sig figs, it also counts. These are obviously placeholders because when I cross them out, that's Jenny's phone number. And now everybody has that song stuck in their head, I hope. If you were, like, born early enough, I guess. But if you imagine a scale, and for our purposes, I'm just going to get rid of these zeros for our scale here. So 8, 6, 7, 5, 3, 0, 0, 8, 6, 7, 5, 3, 1, 0. And our value fell right here. Then I would write down the numbers that I know, which would be these. Oops. I've underlined the wrong number. Which would be these, and also this one. This one's known because we're counting every 10 here, right? So I would write down all the numbers I know, and then I would guess the next digit, which I would say is 9/10 of the way there in the ones place, if this was my number without these zeros. I could put in the zeros, but then I just have a bunch more. Okay. So sometimes your scale will fall on a zero. So for example, if I had this as my scale here, yeah, let's do this. And your result was right here. You would still say, okay, these are counting by tens, and just because I landed here doesn't mean I only have one sig fig, and I only know it's 100. I still know it's 10 tens, and then I would guess the next digit to be that. Okay. Sometimes that will happen. Just be mindful of that when it does. So that's the consequence of this. If you have a zero sandwiched in between two sig figs, you get to keep that zero. That zero is known. Oops, sorry, I thought it was going to the next slide there when I was talking there. The next rule that we care about is called the decimal rule. And the decimal rule is always invoked if you have a decimal. Okay? If you see a decimal in your number, you must apply the decimal rule. So here's the decimal rule. First, find the decimal. Oh, there it is. Okay, so we have to do this. Secondly, underline everything that's not a zero. Those are always sig figs. You always count them. So that's these guys. From what you underlined, anything that's to the right that is also zero is a sig fig. Everything that's to the left is not. So what we see here is that for this measurement, I wrote these zeros right here because I know them. This happened to land right on the line for my measurement, and that measurement just happened to be measuring to this place. And I just happened to get all zeros. I know these zeros are actually here. I have to record them. These zeros have to be included because they're placeholders, but they don't affect my precision. I just have to put them so that I get this 3 right here to start in the thousands place, and not in, say, the ones place or whatever. All right. So those are our uses for sig figs. You should hopefully remember all of these rules for using zero. Here are some more examples. I thought that would animate. Sorry. Let me get my pen. All right. So here, these are digits, so they are sig figs. These are zeros are placeholders, they don't count. These are digits, so they count too. These zeros on the left here are placeholders. All my ones count. The zeros stuck between do count. These zeros on the right are placeholders. This number is right. I have a decimal, so I invoke the decimal rule. This zero is to the right of it, so it counts. The rest are placeholders. All right, so what I want you to do is I want you to take these numbers, and assuming that none of them are counted, assume they are all measurements, tell me the number of sig figs in each number as written. And then down at the bottom here on these diagrams, I'm going to make an addition here. This is a 0 right here, and I don't know why this line is shown, so ignore that. What I want you to do is for these graduated cylinders, A, B, and C, tell me the correct value you should measure for them based on the marks that you see, okay? I'll leave you about 3 minutes to do this, and then we'll go over the answers together in just a moment. Type your answers in the chat once you've got it figured out. Uh-oh, did I hit the wrong thing? I just looked at it and immediately hit a button. You can still see it. I might have accidentally. I apologize. I think I might have deleted your message. I just quickly hit a button. I was like, what is this? It can go away. So I apologize for that. It should still show up on the video though. So which is kind of why I do this, is because I don't know what the hell I'm doing sometimes. Remember that for these values over here on this screen, you can't see my cursor because it's a dot. For these, assume that these are counted. Or, I'm sorry, not counted. Assume that these are measured. Assume that nothing is counted. I know if you play Dungeons & Dragons, your XP is counted. You don't get fractional XP. But for the purposes of this, assume these are all measurements. Just so that you can have an exercise to do. That's what happened. I hit hide on accident. I don't know why. I thought the right option would be to show things. The reason the chat scrolled like crazy like that was because I didn't have it in the front window. Somebody was messaging me, and I had something I needed to take care of. Give me just a second. All right. Let's go over the answers here. So, oops, I wanted color other than black here. Green, sure. All right. As written, if these are measurements, then this is the known number, and these are these are placeholders. So 900 as written would have 1 sig fig if these were all measured. Now, if this was counted, it would have infinite sig figs, because you would know that you have exactly 900 of something. But I said at the beginning, if assume they're all measured, just for the purposes of this exercise. Down here, 90210, this 0 is trapped between 2 digits that are significant, so it's significant. But this 0 right here is a placeholder, because otherwise the TV show would be called 9021. And apparently the show came back, like, what? I don't understand. I don't know who makes these decisions about what should come back on TV. Now, this has a decimal point, which means that we have to apply the decimal rule. So anything to the right counts as a sig fig, and anything to the left must be a placeholder. And then same thing right here. For 500, there is a dot. So here's my sig fig. Anything to the right also counts. So I do have to include that one as well. So be careful with decimal points. Make sure that you don't accidentally add a dot when you do not intend to, because it changes the meaning of the number, even if it doesn't change the value. Likewise, never end a sentence with a number. So, like, if you write, the number of people is approximately 500 dot, that dot could be interpreted as a decimal point, and they would know that, oh, okay, it's 500 with a dot, so it's known to the ones place, or something like that, when that's not what you intend. All right, for these measurements, I'm going to give my best approximation here. So this measures marks in the thousands place. We could say that we have 0,000. And then I would guess the next digit, which would be, oh, it's about halfway, so it'd be like 5. And then I need placeholders for that. Now, obviously, that's not how we write numbers. We don't put zeros in the front when the number is greater than 1. So this would be the estimate that I would put, 500. You could also put 400 or 600. Those are approximately the same thing with this scale. You just got to get close. Over here on scale number 2, or B, the lowest mark is 500. I'm going to guess the next digit, which would be the tens place. I'm going to guess that to be like 4. I need a 0 for a placeholder. Oh, I forgot my units. There we go. And then graduated cylinder C, I know that 5 and 4 are right because that's the lowest mark. I don't know the ones place. We have to estimate that. I'm going to guess 4. Could be a 5. Could be whatever you want it to be. That's fine. I can't write more digits than that, though. I can't put any decimal points because I don't have enough marks to tell me that. So writing 540.0 or 540.00, that implies that I know those zeros to that level of precision. But with these graduated cylinders, I just don't. I need marks to be every 0.1 or so for that in order to get that information. All right. So if you have questions about that, let me know, and we can go over those. Otherwise, let's continue on. That's sig figs. Hopefully you remember all of that as review, because now we're going to use them for doing math. If you have taken 140 or remember the rules for addition, subtraction, and multiplication, division, they are exactly the same. as they were in 140. They are not the same as each other. They are the same as they were in 140, so nothing new there. Let's do some examples, just to review. Whenever you do addition, you cannot treat these blank spaces as 0, because in a measurement, they could be any number. If I had a measurement that was 352.826419 in reality, but I didn't actually know that because my ruler stopped here, it stopped at the ones place and I guessed that digit, I don't actually know these numbers. That said, they would still impact my addition, and therefore I need to treat my addition with that in mind. So when I add all these numbers together, like I normally would, and I literally just did this problem earlier and I don't remember the result. I think it's 535. 12, 13, 5. Yeah, okay. This is the result I would get if I typed it in the calculator. But these numbers... Oops, that's the wrong color. I don't want to highlight in black anymore. I want to highlight in yellow. These numbers affect our result. Question mark plus 1 is not 1. That's a question mark. Likewise, 8 plus 4 plus question mark is not 2 or 12. I don't know what it is. It could be anything. So those numbers that are in yellow don't get kept. I only keep the other numbers. That said, any digits that we do know do affect the answer. So what we're going to do is we're going to add straight down like we've always done. Report a number. And then we're going to consider how many sig fig places are available in each digit. This goes to the tens place, this goes to the thousands place, and this goes to the hundreds place. What we're going to do is we're going to look for the first place, starting from the right and going like this over towards the left. We're going to find the first place where there is a sig fig in every value that we are using. So looking right here at the thousands place, I can't do that because I have a question mark here, so I can't use this number. Let's look at the hundredths place. I can't do that because I have a question mark here, so I can't use this number. Let's look at the tenths place. I can use this because all of these numbers are known or reliably estimated. And from then on, it's also true. So I can keep these numbers. That's what I will report as my answer. Okay? So addition and subtraction care about decimal places. Okay? So be careful. All right. On my next slide, it's going to go through that again and do the addition and then round. So there you go. I'm going to give you a few more examples to do, and what I want... Well, actually, we'll go over these examples together. Let me put this on the previewer. That was close, but not quite. Where did my problem go? Oh, for some reason it was hiding. Okay. So I'm going to take that number, 400... Oops, not 400. 4.83. I'm going to subtract 0.7. Make sure to line up our decimals. I'm going to treat the subtraction like normal. And then we're going to start looking for which is the first place coming from the right that has a sig fig in every spot. All right. Let's look at the hundreds place. Oh, there's no sig fig in this value in that spot, so I can't use it. How about the tenths place? Tenths place is good. So I will round my answer to the tenths place and report that as my result. And that's what we should get. There you go. Forgot to put the next problem up there. All right, so let's do the next one. We're going to do the same thing. 7300, 139.228. Sorry, is that a 9 or an 8? Where? Do you mean this one right here? This should be an 8, if that's what you're asking. Unless you meant this one right here. This is a 4. It should be 8. 4.83. That's what I have, right? Yeah, everything looks good. Ah! Didn't crop how I wanted it to. Oh, you meant the previous problem on the previous slide. Let me go back to that. I might have made an addition error. That's definitely possible. Oops, I'm on the wrong screen. We'll go back to check that in a second, but let me finish these examples real quick. Sorry about that if I made a mistake. So we're going to add as normal. This one I can do because these are not a bunch of numbers. And then let's apply the addition rule. So do I have a number? Nope, not here. I don't have this. I don't have that. So I can't use any of these. But when I get to the ones place, do I know this number? Is it 0? Or is that 0 a placeholder? What do you think? Is that 0 and 7,300 known? Yeah, they're both question marks, right? Because these are placeholders, so that means that I don't actually know what they are. It could be 7,267, but that would get rounded to 7,300 because this is the only sig fig that I have, or these are the only two sig figs that I have. So I don't get to use either of these numbers. This is the first position, the hundreds place, that I get to report. And so that would mean my answer would be reported as 7,400. Okay? Because I go to the hundreds place. This is the first spot that has a sig fig in every spot. All right, let me get the last one example here for this. And then we'll go back and see what the issue was for that previous one. I didn't hit the button. There we go. Well, like, where did it go? Okay. For the last one, let's add 3,000 and then 6 together. And you can already tell that this is kind of weird in terms of a result. So we're going to do the same thing. So I'm going to look here. Can't do it because these are all placeholders. So I can't do this one, can't do this one. What happens when I get here? Whenever you have leading numbers in front of something, you know that these are all 0. But those are not shown because that's not how we do numbers. But we know for certain they are 0. So we can add a 3 and then this 0 to get this 3 and know that that's correct. So I'm going to round to the thousands place. So in all of these science classes that we take, 3,000 plus 6 is 3,000, which is like, what the hell? Like, that seems ridiculous, but it makes sense if you consider the following. Let's suppose that I have a giant bin that holds tons and tons of stuff in it. And so I have this many things in there. And then what I do is I have a little hatch at the bottom. So it's right here. And what I'm going to do is for however many toys that are in here, I'm going to have 11 toys removed. And so this will summarily sink down a little bit. So it might go or something like that. How many toys are in there now? Well, the measurement didn't change enough for us to change our estimate. We would still guess about whatever this number would be, which would be like 29,000 or something. Taking away 11, it was too small to affect it. Another example, let's suppose you win the lottery. And you win $670 million. But you're new to this being rich thing, so you celebrate in the only way you know how. You go buy a Big Mac for $6.99. How much money do you have left? Is it $669,999,993? Or do you just say, I don't give a shit about these numbers anymore. I have $670 million. There's a reason that when we write stuff with really big numbers, we just put the capital M there. Because that M means, man, I don't give a shit about those zeros past this. You could spend $100,000, which is like a lot more than I make a year. And it wouldn't even affect the precision of your answer. So when you make small adjustments to really large numbers, it doesn't affect them. And that's why you get the same result. Because the tool being used for the crude number, this is the crude number up on top, is so poorly estimated that these more precise numbers can't affect it. It just gets rounded away. All right, so let's go back and see what my issue was here. Oh, yeah, I'm an idiot. That's why. You know why I wrote 5358? Because I was thinking about it that, wow, those are the last 4 digits of my phone number when I was growing up. And for some reason, I wrote 8. Yeah, no, I just wrote the wrong number. I apologize. All right, so those are our addition examples here. Any questions, let me know. Let's do the multiplication examples, and I'll give you the sample exercises, and then we'll take a break. So multiplication, same deal as in any algebra class. You would just do the multiplication as you've been trained. So the area of any rectangle is just its length times its width. So let's just times those together. But if you consider the quality of these measurements, this is much more precise, and this is very rough. So the rough number is going to affect our outcome in this way. Remember that multiplication can be expressed as, oh, I'm going to multiply a bunch of numbers, and then I'm going to put an X down and move the places over. And then when I'm done, I'm going to sum everything together. So these X's are just 0 for that purpose, if I knew all of these numbers. But if I expand these out to the same number of decimal places, some of those numbers become question marks, and they affect our precision at the end of the day. So I get a bunch of question marks down here that I can't use. And at some point past that, those are the numbers that I can. We all remember long multiplication. We're not going to do that because that's tedious and we've moved past it. This isn't 3rd or 4th grade anymore. So now what we're going to do instead is we're going to provide just the results of that. We're going to take our numbers and times them together using a calculator, and we're just going to spit out the number that it gives us. So these sig figs rules apply to everything you do in this course and a science course. Okay. So at every juncture where you are entering a number into anything, you should consider sig figs. Because we are always working with measurements in the things that we do. Now, if you are at trivia night, maybe that's different, because trivia night would not be like a place to use sig figs, nor would be like, say, money, if you're going to buy something at the supermarket, you would not just truncate the value of your groceries to the nearest dollar or something like that and then just give them the money and let them keep the change. Like, no, you don't do that. But as far as like measurements are concerned, in any operation we do in this class, you're always going to apply sig figs. So these are not just like, oh, this is a thing that exists. Hooray, that's neat. We're going to use this for everything from now on, and you'll be responsible for it. So what are the multiplication rules? What we're going to do is we're going to count the number of sig figs in each value. So this top one has, all of these are sig figs because none of them are 0. So there's 6 sig figs in that one, and then there's 2 on this bottom one. So there you go. Then we're going to do the multiplication with the calculator and just print the number it gives us. Once you have done that, your answer will have the fewer of the sig figs that your multiplicand had. So between these two, I had 6 and 2. Which is fewer? 2 is. So my answer will have 2. Now, which 2 sig figs do you keep? It would not make sense for me to keep these and report my answer as 4. 14 times 6 is not 4. So that doesn't make any sense. We're not going to do that. Instead, we go in this direction and we keep the first 2 that we have, and then round as appropriate. This would be the answer to this problem. Now, I don't really care much about bankers rounding, so bankers rounding is round to even. So what that means is that if you land on a 5, you round towards the nearest even number. You can do that if you want. My answer should be set up so that it doesn't matter if you do bankers or regular rounding. Bankers rounding is useful if you have lots and lots and lots of digits, because it provides a more statistically sound result that doesn't drift away from where your average should be. Problem with bankers rounding when you only have one data point, which is what we're working with here, is that we're not averaging our answer. We're just doing the problem. And when you use bankers rounding, you tend to get more error than you save over averaging. So I don't care about bankers rounding for this purpose, because we're not doing like an assessment where I'm collecting 75 data points and then averaging them or something like that. So round however you feel comfortable. Excuse me. And that'll be good enough. I have some multiplication examples for these. I want you to report the answers that you get, so I'm going to leave this example on the screen for you to do. I'll give you a minute to do it, and we'll report the answer in just a second. Okay, you got 6.5. So when I punch this into the calculator, I get 5.4336 times 1.2. I get 6.52032. Let's keep the first 2 digits. There you go. I have another slide with these coming up, so I'm just gonna skip through these. But if you do these examples, you'll see that I am basically just keeping the number of sig figs. So this is 5 sig figs, 3. That's the lower one, so my answer has that many. This is 1, 2, 3, 4, 5, 6 sig figs. This is 1 sig fig. So my answer would only have 1 sig fig. Now, how do you know when a number is exact or not? I have to tell you. So if it's not specifically stated as exact, it must be inexact. Okay? I don't know what tool would give you a measurement of 2 with no other information, but for the purposes of this example, that's how it works. Okay? Now, the only exception to a single-digit number being written as exact is 1. So if you see something like this, this 1 is always implied to be exact. So when you see a conversion that has a 1 on the bottom or a 1 on the top and the other number is like 3 or 4 sig figs, you may assume that that is an exact number. Okay? Because otherwise, any calculation you do would be 1 sig fig, and you'd lose all your precision. What this statement right here is saying is that exactly 1 kilogram is in 2.204 pounds, approximately. And we'll see more of those examples later on today when we start doing conversions. The last thing to note, your calculator is very bad at doing sig figs. If you were to do this operation in your calculator, it would spit out this number. And you can try that if you'd like. But when I do this addition, this is the actual number I get. And applying sig figs, I would have to keep to this space anyway. So be mindful that when you are typing something into your calculator, especially addition or subtraction, you may have to provide extra zeros to have the right number of sig figs. This comes up in labs all the time. If you have 2 measurements and they both happen to land on the last digit and you're subtracting, that digit disappears when you put it in the calculator. But you still need that 0 because you know it's 0. Because you're doing subtraction. You know down to that place. There is one more thing, actually, to mention. I forgot about that. And that is, what do you do when you have combined operations? And that is that what you want to do is you want to do them stepwise following the rules of algebra. So that's, please excuse my dear Aunt Sally, or as I like to say, please excuse my dumbass sibling. That's my favorite one because I remember it that way. It's funny. What are these? These are parentheses, exponents, multiplication, division. These are grouped together. And addition, subtraction. Those are grouped together too. You want to do your operations in this order? Anytime you switch operations, you have to consider sig figs. Okay? So be mindful of that because you get some weird results. For example, this number at the end when we're done is only going to have 2 sig figs. But this number is 3 sig figs, and this one is 5, and this one is 4. Where the hell does the 2 come from? It comes from this. So when I do this subtraction, I should get that. I believe that that's right. 7981, 17 is 8, 2 zeros 2. Okay. How do you add more zeros? You just write them in or type them in. Well, I mean, so when you write your answer or report it somewhere, you have to put the zeros in yourself. So for this problem, I got to do the parentheses first, which makes me do the subtraction. So this is the result that I get, but when I consider sig figs, I can't do these numbers. So I would round to here. So this is the result that I should report. If that was all I was doing, I would just say, okay, there's my answer, I'm done. But if I'm using this number for future calculations, then maybe I want to preserve this information because it comes from numbers that are known, right? So what I'm going to do is I'm going to mark that this has 2 sig figs. I got the wrong thickness of pen there. That's okay. And then what I'm going to do is I'm going to take this number and put it back in the calculation. And so you can indicate this by underlining it or whatever. And then we'll go do the division. And when I punch that into the calculator, I forget what this one is. I literally just did this problem. I get 1.06744, which I would round to 2 sig figs right here because that was all I got from the previous problem. And this would be the answer I report. Now, if you didn't preserve these numbers here, and you just put this into the calculator, in this instance, you actually get the same result. I got 1.06100, which still rounds to 1.1. What's the best way to do this and get the most accurate answer for all of these operations? Because you can see, if I was doing like 7 or 8 operations in a row, I would slowly accrue error, and I would then be off in the last digit. Well, for one, if you preserve as many digits as possible, which would be these, in your calculation, then you're going to have the most accurate result that you can because these two numbers come from something that is known. These are known right here. It's just that they're added with this unknown, so I lose that accuracy. So obviously, these numbers aren't reliable, but we could tell that they're kind of sort of, there's some information in there. And I could keep that and keep propagating it. But at the very end, is it really going to matter? What's going to happen is if you keep everything or if you don't keep anything, you just truncate every time, this is the last digit that will change, and it changes very slowly. So you might end up with 1.0 or 1.2 later on, but you will still be close enough to the correct answer that our uncertain digit will encapsulate the correct result. Okay? So in short, it doesn't really matter for our purposes, especially since we're not going to be chaining that many calculations together anyway. All right. That was a brief review of how to do sig figs for calculations. There's our practice problem here. I'm going to leave these for after the break because we're due for a break now. So when we come back, we will do these I will have you do these exercises. You can do them during the break if you'd like to. But I'm not going to require that. So go fill your water off. Use the restroom. Pet a cat. I don't know where my cats are. I'm going to start the timer and get the music back up. Where's my Paradise Killer? There it is. All right. See you in 10 minutes. That was close. Close enough, right? Alright. I'm going to put this screen back on. And then I'm going to allow you to do these problems. If you have done so already, go ahead and type your answers in the chat. We'll go over the answers together in about 5 minutes or so. So go ahead and do these, and let me know when you're done. All right, it looks like people are getting close, so I'll give 1 more minute to just finalize your answers. All right, let's go over these together. I am in the wrong window. Oops, hold on. There we go. And I got to clear all this. All these shenanigans off of my screen here. There we go. Okay. So for this first one, I need my stylus. I have the wrong color. Hold on. 019 times. Alright, so this number has 2 sig figs. This number has 4 sig figs. And we're doing multiplication. So I'm going to punch that into the calculator real quick here, because I haven't actually done that. And I get 0.040641. And for that, since 2 is the smaller number, I only get to keep 2 sig figs. So I'm going to round to 0.041, and that's my answer. For the second one, we're doing division. Same principle. 2 sig figs. Oops, that's not the right spot. This is 4 sig figs. This is 2 sig figs. That's the smaller one, so whatever my answer is, I'm only going to keep 2 sig figs. So I got 2.029512195. I'm only going to keep the first two. 2.0. There you go. For this next one, now we're doing addition. For addition, I'm going to do those over here. Let's set up everything vertically. 20.3, 0.009. Let me get my other color out here. Oops, that's not the paintbrush, that's the magnifier. So, if I just put X's in all the positions that these are placeholders, I end up having to come all the way over to here. This is the first one that works, so I'm going to round to that spot, which means that the answer I report is 3,000. Because those other numbers are just too tiny. They do not impact the magnitude of my result enough to change it. For this next one, we're doing subtraction. I'm going to subtract 13 minus 6 is 7. Now you'll notice that I went from 3 sig figs on both of these to 2 when I did the subtraction, But when I apply the addition rules, everything checks out in the hundredths place, so I can keep all the numbers that are written there. And that's the correct answer. When you do subtraction or addition, you may lose or gain sig figs. So make sure you're applying the correct rules and you're not trying to apply the multiplication rules to everything. This information is not relevant to addition or subtraction. We don't care about it. We only care about what place we're going to. I gotta get these guys out here. Let's see. I'll just put the last three on here. That's supposed to be a decimal, not a comma. It looks kind of like a comma. There we go. We're doing multiplication, so we care about sig figs. Each of these has 4, so my answer is going to have 4. 6 times 2 is just 12, though. If you punch this in your calculator, you only get 2 digits. You have to add the next 2. Okay? And that would be the correct answer. Now, interestingly, you might look at this and think, well, wait a second, multiplication is like doing addition of the same number over and over. So couldn't I just add 6.000 to itself a second time? And the answer is, yeah, you could if this was exactly 2, but this is approximately 2. So since we're not certain that this is a whole number, I cannot apply the addition rule here and go 6.00 plus 6.00 and add this extra 0 that I would get as a result there. Okay, so if we're doing multiplication by 2 numbers and both numbers are inexact, you have to do it this way. What else do we got? We got a combined problem. I'm going to do what's in the parentheses first. Let's add those together. 18514. Sorry, that's supposed to be an 8. Let me X out my positions that don't have sig figs, so I can't do this one or this one. This is the first one I can keep. So if this was where I was ending the problem, this is where I would report it. I don't know why this dot isn't appearing. There we go. And my result would have 3 sig figs, so we're going to report that. But I'm going to carry the whole thing over for the next part of the problem, which is to do this to it. Noting that this only has 3 sig figs, if that matters. Turns out it doesn't. My answer should only have 3 sig figs when I'm done. So we'll punch it in the calculator, see what we get. I got 0.1621659. So I'm going to report this as my answer. All right, and then for the last one, I have parentheses around the division, so I'm going to do that part first. When I punch that in the calculator, I get 14.58333333. And the 3's go forever. This is 5 sig figs, this is 2 sig figs, so my answer should only have 2 sig figs. So if I was reporting it, that's what I would report as the answer. But we have more stuff to do with it, so we'll just carry it all over. I'm going to subtract. You'll notice that in almost every case, carrying the digits over doesn't really matter. Because in this case, nothing past the ones place is useful. So this is where I'm going to report my answer to. So I would get 14 minus 11 is 3.58 whatever, which would then round to 4. And that's my answer. Let me put a dot here just so we have that. Looks like most people had no trouble at all with those. That's to be expected because you've already done all this last quarter. So good job. All right, and I believe that's the end of that section. Oh, we have precision and accuracy to talk about here. I thought we already talked about this, but I'm starting to get slides mixed up because there are just so many slides in these chapters, and we do a lot of these in 140 also. Okay, so we're right here. All right, so for the next little bit, for the rest of the lecture, what we're going to talk about is we're going to show what happens when we take all of this information and then synthesize it together into lab results. Normally, if you were in the laboratory doing experiments, you would not rely on one data point because the odds of you making a mistake in one trial are fair. They're not guaranteed. You might have done it correctly, but there is the potential for error to occur in any possible form. You could get a systematic error or a random error or whatever. So a good strategy is to take the average of our results to try and minimize out the effects of random error. You can't average away systematic error, unfortunately, but you can definitely notice it when comparing it to a true value. So we can at least minimize some degree of our error by taking the average of different values. So what we're going to do is we're going to look at some various results from different examples. These specific ones are from the textbook. These are 3 machines that dispense 296 milliliters of cough syrup into a bottle. And so machine number 1, machine number 2, and machine number 3 are whatever state they're in. They might be old, or might have been recently repaired, or might have been recently calibrated, or whatever. And we're going to try and examine them by looking at their results. So this is the expected outcome. We should have an average of 296. So let's look at dispenser number 1, and right away you can tell everything is below the target value. If I look at this average here, the average ends up being 284.0 or something like that. Oh, this one's a lot lower, actually. I thought that was an 8 up there, so let me actually get you the average. So 283.3, 284, 9, 84. And so I got, oh, I didn't divide by 5. Oops. I was like, wow, I got a really big number. I got 283.9 was my average. All right. How does this compare to the target number? How did we do? Is this close to the target number or not? I'm speaking to you from 10 seconds in the future, so I'm going to assume that you're typing, oh, it's not close in the chat, and that's going to appear right about now. You can't see me, but I'm like casting spells at the screen to make the chat move. Maybe nobody said anything. Whatever. That's fine. So these results are... There you go. Thank you. I'm a little farther in the future than I expected. Okay. So these results are not close to the target answer. So we would say that this set of data is not accurate for dispenser 1. But let's consider how well calibrated the machine is with regards to dispensing the same sample every time. Yeah, there's a lot of chat lag. That just happens with YouTube, unfortunately. If I consider how close these all are together, they're quite close together. And so what we would conclude is that these values are precise. So we have 2 rubrics here. We have accuracy, which is how close you are to the target, and precision, which is how close they are to each other. So let's use that for dispenser 2 and dispenser 3. Is dispenser 2 accurate, precise, both, or neither? What's your opinion on that based on the numbers that you see? And I'll give you a second to think about that. Type it in the chat when you got it. Now, how do you tell if it's accurate or not? Because some people say it's accurate, some people say it's not, some people say it's sort of accurate. Well, the way that you determine if it's accurate is you take the average. So find the average. Oops, I again forgot to divide by 5. And the average result that I got was actually exactly on the target. So this machine is accurate. However, it is sort of all over the place. It's not precise at all, right? I actually should change the color of this so that it matches. Because our accuracy stuff should be in black for this example. That's the wrong pen. There we go. So this is accurate. But is it precise? How do you determine precision? Precision has to do with standard deviation. Again, this is not a statistics class, so I'm just going to look for the biggest one and the smallest one, and I'm going to say, wow, that's a lot of error. That's like 5 difference, which would be, what's 5 over 300 or so? That's, I got to type it in the calculator. That's like a 2% difference in measurements. That's significant. So we would say that there is a large deviation and that these are not precise. Okay. You should be able to tell by looking at something if it's precise or not, just based on how close they are. If they fluctuate in the last digit only, that's a good sign. If they fluctuate in more than one digit a lot, that's not a good sign. Now, over here on the first one, we have this weird data point that's a fair amount lower. It's like 0.8 different. But 0.8 still falls within the last column. Here, the difference is like 4.9 or 5 point something. Let's look at number 3 over here. You could see that this average is going to be very close to the correct number. And the deviation between them is very, very small. So this is the lowest one and this is the highest one. These are only off by 0.2. So these are precise. And accurate. So dataset 3 is the best machine. This is probably just recently calibrated. Dispenser 2 probably hasn't been calibrated for a while. And dispenser 1, my best guess would be that whatever cell holds the liquid before dispensing, somebody put the result like hold this much. They calibrated it wrong. They told it to put 284 instead of 296 or something. All right, so these slides will just go through that, and there you go. Now, how do you relate precision and accuracy to real things that we can ascribe? So precision tends to relate to random error. Not random. It's not French. Random error. Whereas accuracy tends to be related to systematic error. Random error is a random error that occurs and can occur because of any number of things. Maybe like the dispenser is clogged or something like that. And so part of the sometimes the liquid goes through cleanly, but other times it gets stopped up and the timer that stops the liquid from flowing goes off too early before it can all dispense. Like something like that, I guess. That would be random error. Systematic error would be the error occurring the same every time. And that would be, oh, I set the bar on how much I should dispense too low. And so every single time it will be too low. And I believe my slides later on go over this a little bit more. Yeah, here's some more systematic error examples. An example of systematic error would be if you were looking at a graduated cylinder incorrectly. This is the correct way to look at it head on. If you look at it too low, then you get a result that's too high because it ends up hitting the back of the graduated cylinder, and you see a result where the meniscus crosses over at a weird result. And if you're looking at it from above, you end up looking down at it, and the meniscus will hit a number that's too low. If you are always looking at your graduated cylinder too high, you will consistently get the wrong result in one direction. The accepted method of doing this is to look at it head on, because there's only one way you can do that. Okay. Now, if you make the same mistake every time and your answers are always too low, then you're going to get a systematic error. And all of your results will be too low as a result of that. All right. Random errors are random. They come from all sorts of different places. It's very hard to pin down random error. This can be things like heat, air pressure changes, air current changes. Like if the fan is on in the laboratory and like it blows over the balance, that can change the number that is shown on the balance. If people walk by, that causes random air currents, which can change the balance. If you're holding glassware and then setting it down, its temperature will not be uniform with the rest of the room and could be hotter or colder depending on what you have recently picked up. All of those things can affect the results, but in an unpredictable way. If you do your experiments multiple times, then the odds are that you will get an equal number of results that are too high. Like if this is your target number, like this is the true value, and your results are like this for your various trials, your random error is going to get averaged out to be closer to the true value than any one individual point would be. Whereas if you had systematic error, and I messed up my colors for this, but that's okay. If you had a systematic error, you would get the same deviation each time due to that error. And so you can't average that out. Your average would be still up there. And no amount of trials and averaging will remove that error. You will still be off from the correct answer because of that systematic error. This is just a visual diagram of that. You've probably seen this before. Accuracy is just how close your points are. Or, I'm sorry. Precision is just how close your points are together. So these sets are very close together, which makes them precise. Accuracy is how far away you are from the target. So this is not accurate because there's a big deviation. These are very close to the target, so they are accurate. Remember that we take the average when we consider accuracy. That's not a very good average. So the average of this one would actually be right around here, which ends up being quite accurate. But because there's so much scatter between those targeting marks on there, or bullet holes, or whatever you want to call it, the precision is very low. And we already talked about what can be averaged out, so there's that. Okay. What do I care about in the laboratory? This slide is only relevant if we were actually in the laboratory. The most important thing to be is precise in the lab. Precision is an indicator of skill and technique. And so if you were in the lab doing these experiments repeatedly and you got the same result every time, then that means you're being precise, or at least a very similar result. If you made one mistake somewhere, but you kept making that mistake, then we could debug that, and then you would be fine. So accuracy is not as important. We can diagnose accuracy. Diagnosing precision is much harder because you could be doing any number of things, or you might just be careless. But we're not doing lab because people can't wear masks and stay at home. So we're not going to worry about that so much. So whenever you actually get to the lab, that's when we will worry about that. How many more slides do I have? Do I have enough time to really start math here? I have 7 minutes to do this. You know, let's just start with math on Thursday. We'll talk about math. We'll do the calculations on not Thursday, sorry, Wednesday. We'll do the rest of Chapter 1 on Wednesday, and then your quiz will get posted. And we'll move on to Chapter 2, which actually has new stuff mixed in with old stuff. So we're going to call it a night for here. Yeah, I'm very passive-aggressive. That's me. Wes is passive-aggressive, the personified, I guess. Whatever. Whatever, right? All right. I want to thank everyone for coming out to the lecture. As always, it is a pleasure to have everyone here. Let me know if you have any questions about any of the content, about sig figs, about the practice problems in the text, or whatever. Send me an email. I will get to those emails after this. I'm going to go make dinner, and then I will answer emails because I'm starving. But I will get to those questions tonight. And then post questions if you have them in the Discord to myself or other students. Other students might know the answers and be able to get back to you before I do. So use all the resources that you have handy. And I will see you next time tomorrow. Have a good night.